So in the last couple of years, I've noticed there's a big confusion among teachers about the meanings of these basic science words. Funny enough, I've never needed to do a video on this, and so now I'm putting one together just to clear everything up for students. So it doesn't matter if you're in year 7, 8, 9, 10, 11 or 12. This is really quite important, especially for year 12s, where you need to justify your changes using these words. So state the word and explain why your change improves that. It's also useful to describe errors in the data and errors in the method at the end as well. So get these 4 words clear, and then everything else should flow. So ironically, the time when QCAA has actually quoted a source, I'm quite happy with these definitions. So reliability is getting the same results with the same experiment. Validity is you're actually testing for what you say you are, and that's fine. What they've done here, unfortunately, is they've mixed up accuracy and precision and called them basically the same things. I'm happy with all the other stuff, but when they start saying that precision is accuracy and accuracy is precision, then we've just erased the word, really. And so I think one of the big things is trying to a size fits all. And so I think it's a useful place to start to realize chemistry and physics are called the hard sciences because they have hard data and they're always trying to find the truth. So they have all the variables are very tightly controlled. So there's not really an issue with reliability. Of course, it's very, very reliable and valid. We can always usually get the answer. It's usually just an issue of this person, well, the truth is 5.01 or something, and someone actually got 5.0 plus or minus 0.05 or something. That sort of issue. It's like, well, that's not probably a very good number, but maybe if I make it, the answer is 5.00, then this one here is more precise. They're both got the error within the range. And that's the sort of thing we do in chemistry and physics. We don't need a large number of trials. Sometimes we can get away with just 2 if you're doing a titration well. And so it's all about accuracy and precision. Okay, now for biology, it's an endless number of uncontrolled variables and systems that even now we don't fully understand, either psychology or the way the body works or the interactions, positive and negative feedbacks. And so we get around that by doing large numbers of trials. So obviously for diet and stuff, you can see in the newspaper, they see tens of thousands of trials and sometimes meta-studies. And the only way to really deal with that is statistics. And even then, we don't really trust the answers. So the reliability and validity are really difficult because you just can't control your variables. And so we talk about standard deviations and how confident we are there is a difference in the average and what the average is. And so it's a completely different way of doing things. So that is where a lot of this problem occurs. And so moving on, just the definitions I'm going to give you for accuracy. So accuracy is how close it is to the true value. So what you can see here is this is the same mass. You don't actually know which this 100-gram mass, whether the truth is 100.69, 100.61 going by this, but I'm just demonstrating to you that one of the balances is more accurate than the other. So one of them has a greater accuracy than the other. So moving on to precision. So precision here is, these are the gold standard definitions I want you to know for these ones. So I'll just go back over there. Accuracy is how close it is to the truth, all right? And precision is how close the readings are to each other, how much they're going up and down. And so for this one here is only measuring to 2 decimal places, whereas this is measuring to 4. So this is more precise. And that sort of indicates that this one's going up and down quite a large amount, and this one's going up and down quite a small amount. And so this one here has smaller uncertainty, better precision. Okay, now moving on to reliability, just simple, clear definitions. You can repeat the values. Okay, so just look at the way that your experiment has gone, whether you've really controlled the controlled variables. And that's probably something where you can start talking about how reliable it is, depending how extreme that is. And lastly, validity. Validity, it's very uncommon for an experiment to be invalid. It's actually hard to think of ones. So this is one that did actually happen. And so they were thinking that cutting this increases the surface area, which it does, this tiny, tiny, tiny bit, 1, 2, 3, 4, 5, 6, 7, 8, almost insignificantly. All right. And then when they put it into a reaction, they all stuck together actually. And so the surface area was actually massively reduced. And they got crazy results because of that. So what they're actually doing is massively decreasing the surface area and then saying that they were increasing the surface area. So that experiment was completely invalid. Okay, so make sure you get the main reason and the main problem, whether it's accuracy, precision, reliability, and validity. The confusion comes not fully understanding what the four things are. The other confusion that comes in is often one of these things will then affect another or even affect all of them. And so you've got to really hone in on what the real error is. Is it the validity or the accuracy or the precision or the reliability? And then that may or not have a knock-on effect and affect the reliability, validity, precision, or accuracy somewhere else. Okay, so it's not all that simple. It's just get your basic understanding first, and then work out which one is the most significant and the primal cause of the error. And if it's two different things that separately, make sure you explain that when you're doing your improvements or analyzing your errors. Okay, I hope that's helpful. Thank you.